OCPWM.C is a very simple program that demonstrates how to use an output compare module to generate a pulse width modulation signal. We're going to use timer 2 as our timer base using the peripheral bus clock as input. In this first line here, we're going to set up the prescaler for timer 2 to be 4. So we basically divide that 80 megahertz clock by 4 to get a 20 megahertz clock. And then we're going to count up to 1999, so 2,000 counts before timer 2 rolls over. So that means the period of our PWM signal is going to be PR2 plus 1 times the prescaler times 12.5 nanoseconds, which gives us 100 microseconds. So we're going to create a 10 kilohertz PWM signal with a period of 100 microseconds. And this is a pretty typical frequency for PWM signals to control motors, for example. We're going to set the initial value of timer 2 to be equal to 0. And then we're going to set OC1, output compare module 1, which will use timer 2, to be in PWM mode without a fault pin. So there's no fault input. So this is going to allow us to create this continuing pulse train that is pulse width modulation. The next thing we do is we set the value of the special function register OC1RS. This is the one that we usually change if we want to change the duty cycle of the PWM signal. Only for the first iteration are we also going to set OC1R, because once we turn on the output compare module, OC1R will be a read-only special function register, and all it's doing is at every cycle it's going to read in the value of OC1RS. So if we want to change the duty cycle, we write to OC1RS, then OC1R will read it in, and that actually implements the duty cycle. Then we're going to turn on timer 2, and we turn on the output compare 1, and now the PWM signal is being generated by output compare 1. The next line, all it does is it's going to implement a delay for 4 seconds using the core timer. So if we had an oscilloscope, we could see that the duty cycle of our PWM signal is 25%, because we're choosing to wait 500 counts of timer 2, which is going to roll over after 2,000 counts. We're going to wait for 500 counts before we set the signal low in our PWM signal. So we're going to get a 25% duty cycle. So after waiting 4 seconds so that we can have time to see that signal on our oscilloscope, we just change the duty cycle to 50% by changing OC1RS to 1,000. And then this program is just going to sit in an infinite loop forever, generating a 50% 10 kilohertz PWM signal. Usually, if you're going to control a motor with a PWM signal, what you'd be doing is you'd be updating OC1RS periodically to change the average voltage that an H-bridge is trying to put across a motor. But that's a topic for later.